Next, the third reaction is third electrophilic substitution reaction is Friedel Crafts acylation. Friedel Crafts acylation is similar to Friedel Crafts alkylation. We are going to just change some few things. So basically here we look at the reaction of benzene with acyl compounds. Previously for Friedel Crafts alkylation, it was reaction of benzene with alkyl halides. So this is where benzene reacts with acyl compounds, still in presence of a Lewis acid catalyst or halogen carrier to form acylated benzene. Now the halogen carrier still works in the same way. It has the same purpose. The halogen carrier or the Lewis acid catalyst has a central metal. It has a central metal atom that has vacant orbitals. It has a central metal atom that has vacant orbitals, and this induces polarity, and this induces polarity of the what? Induces the polarity of the carbon halogen. This is polarity of the carbon halogen bond within the acyl compound. This is polarity of the carbon hydrogen bond within the acyl compound. Now here the product is acylated benzene or a carbonyl compound. A carbonyl compound or carbonyl compounds which we call phenyl, form acylated benzene or phenyl ketones or phenyl alkanones. The halogen carrier serves the same purpose as before. It has a central metal atom that has vacant orbitals, and this will induce polarity of the carbon halogen bond within the acyl compound, resulting in formation of an electrophile, that combines with benzene via electrophilic substitution mechanism. So for Friedel Crafts alkylation, I illustrated this earlier on. For example, if my Lewis acid is iron 3 bromide, iron 3 bromide looks like that. Now iron 3 bromide, iron in this compound, iron is a transition metal. Transition metals have vacant orbitals. In fact, that's one of the reasons as to why they form variable oxidation states. Like iron, we can have iron 2 and iron 3. So iron has 2 oxidation states or 2 valencies. So it has vacant orbitals. After it combining with bromine, it has used some of its electrons. Now implying that after it combining, we shall form vacant orbitals. So orbitals that were originally occupied by electrons, they are now vacant after it bonding with bromine. Now, since it is having vacant orbitals, those vacant orbitals can attract lone pairs of electrons. In simple terms, iron in iron 3 bromide is an electron pair acceptor. So since it is an electron pair acceptor, that induces polarity of the carbon halogen bond, resulting in formation of an electrophile which will combine with benzene. Now let me illustrate that in detail. We have our first example. Still, there are two approaches towards the reaction mechanism for this reaction. Now, I'm changing slightly the benzene ring. Recall that we saw that benzene can also exist in that form. Now, I'm only changing the benzene ring, but other things are going to remain the same. So now I recap the two approaches that we saw earlier on. Let me repeat them so that Africans do not complain. So to repeat them, we saw that in method one, we can have our halogen carrier. Now this is the acyl compound. It has two carbon atoms. And in particular, since it has two carbon atoms and chlorine, we call this ethanoyl chloride. Ethanoyl chloride, that is its name. That's why they are called acyl ethanoyl. They end, their nomenclature, they end with that suffix OYL, ethanoyl chloride. So in approach one, I'll write my acyl compound as CH3, then C, there is carbon to oxygen bond. There's carbon to oxygen bond, like that. Then carbon to oxygen double bond. Then this carbon also bonds with the chlorine, like that. Then ferric chloride and trichloride. I have told you that iron is electron deficient. So since it is electron deficient because it has vacant orbitals. So this can donate, and this is a polar bond. So chlorine can take electrons, then donate them to that central metal atom in iron 3 chloride, like that. Then we shall have the following. So this bond is broken, then we form an electrophile, CH3, C, double bond with oxygen, then it is electron deficient. Since electrons have been taken to the central metal atom, then here we form FeCl4. There are now 4 atoms of chlorine with a negative since we have brought electrons there. Now our benzene ring, now is going to combine with this electron deficient species, that one. So this carbon is the one that is electron deficient. Now if we have benzene of this form, I explained why benzene can exist in this form. If you did not watch those videos, kindly you have to go back. So benzene in this form, here we pick electrons from the middle here, because this simply shows that electrons are delocalized. Then donate them to that carbon atom. So what shall we form? We shall have the following. Now since we have taken electrons, this circle is broken. Yes, since we have taken electrons. So we shall write it in this form. We shall have the following. Yeah, like that. Like that. Then I put a plus there as this carbon here. This carbon bonds with that carbon. So we have C. A moment. I think, let me put this up here. It was supposed to be like that. So we have C. This carbon bonds with that C, which carries oxygen and also carries methyl group like that. Then I expose the hydrogen here. So that it donates electrons to electron deficient carbon. So after it donating, it is lost. Minus hydrogen ion. Minus hydrogen ion, as I form the following. So we have a benzene ring with this group COCH3. Then the proton that has been formed, the proton combines with the negatively charged complex FeCl4 minus. So this donates electrons to the electron deficient hydrogen. Then we form hydrogen chloride plus iron 3 chloride plus iron 3 chloride. So my product, I have a benzene ring. With COCH3 plus hydrogen chloride. So that is the example.